In this lecture, we are going to learn about one of the most important purification techniques used in organic chemistry, which is recrystallization. This method allows us to purify solid compounds by making use of solubility differences. By the end of this session, you will understand the scientific principles, the experimental procedure, and the common mistakes to avoid when you perform recrystallization in the laboratory. Recrystallization depends on solubility. Solubility is defined as the maximum amount of solute that can dissolve in a certain amount of solvent at a specific temperature. It is usually expressed in grams per liter or moles per liter. Without understanding solubility, you cannot understand recrystallization. Two main factors affect solubility. The first is the properties of the solute and solvent. The principle is called like dissolves like. Polar solutes dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. For example, sodium chloride, which is ionic and polar, dissolves in water but not in pentane. Wax, which is nonpolar, dissolves in pentane but not in water. The second factor is temperature. As temperature increases, molecules move faster, collisions increase, and intermolecular forces are broken more easily, which increases solubility. A common mistake is to add too much solvent while heating. If the solution is too dilute, no crystals will form when it cools. Some organic compounds, such as alcohols, amines, acids, and halides, contain both polar and nonpolar regions. The functional group, such as the hydroxyl group or the amine group, represents the polar side of the molecule, which is hydrophilic or water-loving. The carbon chain represents the nonpolar side of the molecule, which is hydrophobic or water-fearing. The solubility of these compounds in water depends on the ratio of the size of the nonpolar carbon chain compared to the polar functional group. As the nonpolar part of the molecule becomes larger, the solubility in water decreases. This is often summarized as the 4.5 rule. For example, methanol, ethanol, and propanol are all completely miscible with water. But butanol, which has 4 carbons, is only slightly soluble in water, about 7.4 grams per 100 milliliters. Pentanol, with 5 carbons, has a solubility of only 2.2 grams per 100 milliliters, which is essentially insoluble. The second important factor that affects solubility is temperature. As temperature increases, solubility usually increases. Heating increases the kinetic energy of both solute and solvent molecules, which makes collisions more frequent and stronger. These collisions can overcome intermolecular forces, leading to increased solubility. A common mistake students make is assuming that if a compound dissolves in water when hot, it must also be soluble at room temperature. This is not always the case. Solubility must always be considered at the specific temperature you are working with. Recrystallization is a purification technique that is mainly used to purify solid compounds. The process involves dissolving the solid in a hot solvent and then allowing it to recrystallize as the solution cools. During this process, the pure compound comes out of solution as crystals, while most of the impurities remain dissolved in the solvent. The main uses of recrystallization are two. The first is to separate two different compounds that have different solubilities. The second is to purify a single compound by removing small amounts of impurities. The principle of recrystallization is based on 3 important points. The first point is that different solutes have different solubilities in the same solvent. The second point is that solubility decreases as temperature decreases, so when the solution cools, crystals will form. The third point is that molecules of the same compound have a higher tendency to stick together and crystallize together, which excludes the impurity molecules. A common mistake students make is thinking that recrystallization works with any solvent. In reality, you must carefully select the right solvent where this solubility behavior can be observed. Otherwise, you will not obtain pure crystals. This is the first case of recrystallization, where the goal is to separate two compounds that have different solubilities in the same solvent. The principle here is that different solutes do not dissolve equally in the same solvent. When we heat the solution, both compounds will dissolve completely. But when we allow the solution to cool, the less soluble compound which we are calling compound A, will begin to crystallize first. The other compound, compound B, will remain dissolved in the solvent because its solubility is much higher. The crystals of compound A can then be collected by filtration. If one compound is completely insoluble, the process becomes even simpler. We heat, then filter directly. The insoluble compound will stay on the filter paper, while the soluble compound will remain in the filtrate. The table shows an example of two compounds in ethanol. Compound A has a very low solubility at room temperature, only 0.05 grams per 100 milliliters, but at 100 degrees Celsius its solubility increases to 5 grams per 100 milliliters. Compound B is much more soluble, 1.5 grams per 100 milliliters at room temperature and 15 grams per 100 milliliters at 100 degrees Celsius. This difference allows us to separate them. The diagram illustrates the process. First, both compounds dissolve upon heating. Second, when the solution cools, compound A crystallizes out. Third, we filter the mixture, collecting compound A as crystals on the filter paper, while compound B remains dissolved in the filtrate. A common mistake students make is cooling the solution too quickly. If you put the flask immediately into ice, both compounds may crash out together, leading to contamination. The correct approach is to allow slow cooling so that the less soluble compound crystallizes selectively. The first step is choosing the solvent. A good solvent should dissolve the compound well at high temperature but poorly at room temperature. It should not react chemically with the compound. It should not freeze when cooled to low temperature, and it should have a low boiling point so that it can be removed easily later. The second step is dissolve the solid in the minimum amount of hot solvent. Add small amounts of solvent gradually while heating and stirring until the solution becomes clear. If insoluble impurities remain, remove them using hot gravity filtration with a heated funnel and filter paper. Common mistakes at this stage include choosing a solvent that dissolves the compound even when cold, which prevents crystallization, using too much solvent so the solution stays too dilute, and forgetting to perform hot filtration for insoluble impurities. The third step is cooling. Slow cooling produces large and pure crystals, while fast cooling produces small crystals that trap impurities. If crystals do not appear, you can scratch the inside of the beaker to seed crystal formation. At the very end, place the solution in an ice bath to maximize yield. The fourth step is collection. Collect the crystals using vacuum filtration with a Buchner funnel. Wash the crystals with a small amount of cold solvent to remove any remaining impurities. The fifth step is weighing. Crystals must be completely dry before weighing to avoid errors. Mistakes to avoid include cooling too quickly, washing crystals with warm solvent, and weighing wet crystals. These mistakes either reduce purity or give artificially high recovery values. Filtration can be done using vacuum or gravity methods. Vacuum filtration is fast and ideal for large quantities, while gravity filtration is slower and better for smaller amounts. Both methods retain solid effectively. Finally, we calculate the percentage recovery of a recrystallized sample. For example, if 3G of acetanilide is recrystallized and 2.4G is recovered, the percent recovery is calculated to be 80%, demonstrating the efficiency of the recrystallization process.